We'll get things going now. As I said before, I'd love to welcome you to Big Data. This is the first time we've done a Big Data actual short course. There is a matching course at Charles Sturt called Big Data and goes over some of the things that we'll be covering tonight. So it's a good one to check out. And this should give you a bit of an introduction to what's going on in the big data world. It is a subject that's a little bit close to my heart, having come from the Internet of Things business, where big data is absolutely everything we talk about all the time. As I said before, please remember to set your chat settings to everyone, and please feel free to chat amongst yourselves, ask questions of each other, exchange information. A lot of the really interesting stuff that happens in these sessions happens in the chat, and we absolutely encourage you to chat your hearts out. Questions for Matt and our other panelists, please put in the Q&A, and it's my job to make sure that we get to as many of those as we possibly can during the evening. We will stop a couple of times, or at least once, during the slide sessions to answer some questions that are pertinent. If we think the question's not quite that pertinent, then it may not get answered, or it'll at least go to the back of the queue. Having said that, Lily will be doing the moderation and checking on how things are going. She'll be putting information into the webinar chat and answering some of the questions directly. So I thank Lily for coming along this evening. It's a long day after work to be doing this. And from there, I will just introduce you to Matt Constable. For those of you who have attended our courses, and I'm sure a lot of you have been to a few now, I'm sure you've come across Matt before. He is the absolute guru at IT Masters of all things cyber and data. And welcome along, Matt. How are you doing on this cold evening? Is it freezing out where you are?
Thank you, Shane. Welcome everyone to our course on big data. Yes, it is quite cool where I'm currently stationed at the moment. We've had frost the last couple of mornings, so it's interesting to see in the chat people from all over the place. England, I saw someone from the UK in the Midlands saying it was 28 degrees. So obviously for the English, that would be quite warm, but that'd be a nice autumn or spring day here. So any
I,
case, welcome along everyone this evening. As Shane said, this is our first time that we've run a big data online course. And the first thing I want to say is that, yes, we're looking at big data, but this is really an entry-level online course to give you some real basics. So we're not going to spend a lot of time getting right into the nitty-gritty of it in a lot of detail, but we're going to be looking at the overall concepts around big data, and we'll expand on what we talk about this evening in the next 3 weeks. As Shane said, we welcome any and all questions, and as you said, often the best conversations are those in the chat. So please, if you want to participate or offer something, feel free. Don't be shy. Feel free to ask any and all questions. All right. With all that said, let's progress and get stuck into it. So our first week, we're just doing a basic introduction to big data or big data. Apologies if I say data sometimes and data. It depends on what I'm thinking at the time. But we're just going to look at some of the basics, some of the challenges involved, the different types of data, and then we'll have a look at some of the characteristics of it, which we'll expand upon in later weeks. So section number one, if you like, or module one for this evening is big data fundamentals. And here we're going to have just a brief look at the core concepts and some of the characteristics of what makes up big data. So what actually is it, and what is it made up of? And then try to maybe glean a bit of an understanding of how important it is in our contemporary digital environments, which are so heavily reliant on data. And I think if we just sidestep a little bit for a second and talk about cybersecurity, if we think about what happened in the last week or so with the CrowdStrike issue that happened globally, it's interesting to note that although not a massive proportion of Windows workstations were or Windows devices were impacted in terms of the overall number of Windows devices deployed worldwide, uh, of course, a lot of big end companies who control lots of different online stores or bricks and mortar stores, or a lot of our data that we expect to be able to get access to each and every day, are those sorts of companies that invest in CrowdStrike. And of course, even though in the overall scheme of things, what actually happened was quite simple and relatively small scale, it had a massive impact. And that's because of the fact that we have such a reliance on the online world now, and we have such a reliance on data stores. So it was really interesting to see that actually happen.
I can
Anyway,
confirm that
so big data. Let's have a look at some definitions. So what is it? Simply, it is simply referring to massive data sets that are so large, so cumbersome, um, so complex and difficult to process and work through, that simply using traditional data applications won't work. They cannot handle it. It's the data is at such a volume that we can't comprehend. Our normal everyday applications can't comprehend it. And so we have to take different types of approaches. So if it's almost like you're thinking about it back in the old days, the difference between or even now, a desktop PC and a supercomputer. Okay, what your desktop PC can do is to a certain level, but the supercomputer can handle a lot more. It's on a different economy of scales. And this is the way we need to think about big data. We're talking about taking information data from literally millions of different places and putting it together in a single repository or a singleized distributed repository in order to be able to perform complex searches, use complex algorithms to help build knowledge out of it, to help us solve problems, to help us generate different ideas. So it's a really powerful tool, but it's difficult to get a grasp on what it looks like. And that's hopefully what we'll do by the end of this evening. Now, there's 4 or maybe 6 V's that are often talked about when we talk about big data. And we'll look at these in more depth in week 4 in particular, but this is just a bit of a taster for what we've got to come. So we've got volume, which is the big one. That's the scale of the data that's contained within this massive data set, or data sets, depending on which big data platform you're looking at. There's a velocity. So that's the speed at which the data is generated and which it's processed. So it's generated by all these external sources that we pull into our repository, and then we have to process it. The speed at which data is generated is compounding, is getting faster and faster every year. You think back even just a few years ago, the amount of data that was, for example, generated through our social media platforms is now dwarfed by the amount of data that is now generated through our social media platforms. And this will continue to increase and increase and increase as we progress through history. Variety is a big one as well. There's lots of different types and sources of data. Some of it is structured, some of it is unstructured, and some of it is semi-structured. We'll talk about what those 3 things mean and what they mean in terms of being able to store, analyze, scale, and use big data repositories. Veracity refers to the uncertainty in how good your data is, the quality of it. How much, I guess, trust can we put in that data? So is it really representative of the truth, or is it something, as Mr. Trump would say, is fake news? We then have value, which is the fifth one. So is the data contextually relevant, and is it from a reliable source? So again, this is looking at trustworthiness. And the last one is variability. So we have heterogeneous data. It comes from everywhere, all different types. It comes in different types and different forms. And we have to be able to use it in a way that allows us to generate useful outputs. So what does this all mean? So big data is simply a term that describes a massive amount of data that comes into us from many different sources at increasingly high speeds. Now, as I said, the data could be structured, it might be semi-structured, or it may have no structure whatsoever. And of course, depending on which combination of these we use, we need pretty advanced tools and methods to store, analyze, and then extract information from it. Okay, so we've got the data there, but the data in and of itself may not necessarily be that useful. We need to somehow manipulate it, analyze it, and then extract the information from it, which is what we're really after.
I can give you some examples, Matt. We had a business that was collecting big data for Internet of Things applications. We were storing, I think, 1.2, 1.4 billion transactions a day.
Yeah, yeah, it's a lot, isn't it?
It was a huge amount, nearly broke the billing systems.
Yeah, yeah. It's yeah, it's really, really interesting. It does it there's a It's completely overwhelming. And this is the thing, I guess, is it's quite difficult to initially grasp just how big this actually is. When we talk about big data, the word big brings to mind a certain size, but probably gargantuan data is probably more accurate. Anyway, I digress. So big data types, as we said, we've got three main types that we talk about. So structured, unstructured, semi-structured. They're the different types. We're going to talk about how each type is particularly relevant and why we use each type, and then have a look at some of the challenges, but also compare some of the characteristics of these types. So structured data is pretty common, okay, in certain contexts, but it's data that is very structured in a very fixed, unflexible or inflexible format. It's very organized, it's very factual, and it's very specific to a point. Often it is quantitative, so means basically it's numeric and able to be easily mathematically analyzed using algorithms, mathematical algorithms. So it's a little bit easier to handle. The other thing is there is often some sort of relationship between the different data sets that might be included in the overall data set. So think of relational databases, how we can have multiple databases linked together by, say, a customer ID or a customer name or a date, something like that. So we build relationships with these numerical data sets. And some simple examples here include all of these guys there. So you can see they're all very structured, very specific types of data. It has a number of benefits. Because it is very highly structured and because it's mostly quantitative, it's quite easy to use. It's quite straightforward to understand. It's quite straightforward to understand the structure of it. To be able to store it is very efficient because each of the cells, if you like, or rows or values are of a fixed specific length because it's very structured data. And so because of that, we can set up our storage areas very efficiently with pre-allocated spaces for each of our particular data sets. So it's quite easy to store, quite easy to analyze, quite easy to find. It's also very scalable. We can add storage as needed, and we can add processing power as our volume increases because it will increase at a reasonably fixed or known rate. We know, for example, that if a particular element of our data set is always going to be 1 kilobyte in size, and we introduce another 1,000 entries as a simple example, we're going to increase our storage requirements by another 1,000 kilobytes. Now that's a very small example, but that's an example of how we can scale. It's very fixed, and so we can predict how much storage space we're going to need within a moderate term. Modern systems that process this structured data can easily scale to several thousand terabytes of data and more. Okay, so you can think of that, that's an awful lot of data. So you think kilobyte, megabyte, gigabyte, terabyte. Okay, so we're getting a lot of data, petabyte, exabyte. They can scale up to these massive, massive amounts. The other thing is analytics is really useful here because we've got very structured data and it's stored in a very structured way, and there are many common patterns within these particular data sets. We can use things like SQL, so structured query language, to help us to generate a really directed and specific reports based on that quantitative data. So it's really, really easy to do our analytics on that numerical type data. However, the predefined structure, the fact that we are so structural, can also be a challenge because this data can only be utilized for a very specific intended purpose. So if we go back, we've got an example there, but if we go back here, for example, so if we've got point of sale data, then it's only going to be useful for point of sale analysis or analytics. It's not going to be useful to generate anything else. Reservation systems, the data in that is only going to be useful within the context of reservations. It's not going to be useful for anything else. So as an example here, booking data can give you information about booking system finances and popularity. And that's about it. It's not enabling us to use it for any other purpose. And you'll see how that compares to unstructured in a minute. It's a really big distinction between the two. Another example is it can't reveal which marketing campaigns, for example, are more effective in bringing in bookings to our systems or to our hotel, for example, without further modification. So without somehow changing that data and manipulating it in some way to enable us to glean those sort of additional insights into it. And so because of that, we need some sort of, as it says there, some sort of relational database or relational, um, what's the word I'm trying to think of? Relational relationship. That's repeating myself, but you get the idea. We need to have some sort of relationship established with another form of data, which is then enabling us to look at what we've done with a marketing campaign and see how it relates to incoming bookings. So what we're saying is we need additional data to provide true insights from the initial booking data. So it's very contextualized, very limited, and we have to be quite clever with the way in which we interrogate it and use it to generate useful outcomes. In terms of being inflexible, it's costly and resource intensive to change the schema of the structured data. So once the structured data has been set up, this is a database. It's got this many fields. Each field is this long. Each field is this type of data. We start to populate that with data. It starts to fill up. It gets bigger and bigger. It's really almost impossible to then change that schema afterwards. It's quite difficult. And so it doesn't allow us to then use it as we would, as we'll see in a minute, as we do with unstructured data. And so if we draw this point back to here, it then requires us to create maybe another database file with relationships that help us to glean more information about that original data set. Unstructured data. So this is the big one. This is the vast majority of our data in our big data system. So 80 to 90% is this sort of data. There is no set data model, and it's not ordered in any predefined way. There are massive diversity in the formats that you might see here. And so this is mainly qualitative. So it's not quantitative, which is mainly numeric. Qualitative here, totally different, requires a completely different set of strategies, set of algorithms, set of ideas in order to be able to analyze it. It's also non-relational. Okay, so there's not specific relationships necessarily between any of the incoming data sets. Some typical examples of these ones here. These are just a few. This is definitely not an exhaustive list. There are so many other examples that you think of anything. that you could pull in. Anything particularly from your social media feeds, other websites, news services, whether they be digital or real world news services, all the different methods of communication. There's just so much information that we can pull from a vast array of sources. And as I said, this is where the vast majority of our big data comes from. But there's great value in it. If we compare it, unstructured with structured data, we say we've got ease of analysis. So one of the advantages of structured data is the ability to analyze the information because it's highly structured and it's generally numerical. Not always, but generally numerical. Or if it's not numerical, there's generally a small range of values that fit within the data set. And of course, there's many tools available to analyze structured data. So if you think about if you're using a SQL database, for example, or a point of sale system or a booking system, you'll have tools built into those systems that allows you to analyze the data within those systems quite easily. Significantly more difficult to analyze data that does not have a predefined data model. So if we've got unstructured data, it's a lot harder to analyze it. We have to use different algorithms. We have to use different methods. And so far, there aren't that many proven tools that are available to do this. So collate all these different sources of unstructured data and come up with something that is coherent and useful as an outcome. Structured data is also simple to search because it adheres to predefined rules and predefined structure. By comparison, because we don't have any order within our unstructured data, it becomes really difficult to try to come up with business insights using our normal data mining techniques that have been around for quite some time. So it's more difficult to flesh out what this qualitative data specifically means. And I'll just, after I make this point, I just want to go to another point which might help to clarify a little bit better as well. So searching and analyzing these unstructured data then requires really high levels of expertise, and that's not necessarily in the people, but in the systems, built into the systems that are then trying to analyze this unstructured data. So we're talking about natural language processing, and we're talking about text mining. Now, just to go back to the point I want to make, um, it's between quantitative and qualitative. In cybersecurity, we talk about the idea of risk management and having these two methods of risk management, so quantitative and qualitative. Quantitative risk management is about assigning numerical values, typically measured in dollars or time, to all of the different things, all the different components of a risk. Now, some of those things include things like probability and unknown factors, such as how good a particular mitigation technique might be in reducing the risk of something happening. There may not be any way of knowing that. So we usually say that quantitative analysis on its own is not perfect. Okay, it's very difficult to do to get a definitive answer. Qualitative, however, on the other side is more to do is more scenario based. So we come up with a scenario, we do our analysis, and we come to an end conclusion that is most likely based on the scenario that we derive. And this is very similar in this big data with the ability to analyze it. So while quantitative data is easier to analyze, it might not necessarily give us answers that we're looking for because the data set has that inherent inflexibility inside it. On the other hand, qualitative data has the possibility of giving us all sorts of different answers that we haven't even thought of at the moment, and therein lies a challenge. That first of all, we need to be able to develop tools that can have a tool set that enables us to not think, but discover all of the different solutions that are built into within this data. The ideas are there, the solutions are there, the answers to our questions are potentially there, but very difficult to find. Very difficult to find. And last one is storage. Now, as I said before, with structured data, it's a little easier to think about or to predict where your storage requirements and processing requirements are going to go over any given period of time. But with unstructured data and the amount that's coming in, more difficult, almost impossible to predict. So you think of it, if we think about the different data types that we talked about before, and just these few here, which is not exhaustive, text files, for example, are much smaller than video files. Images can range in size from very small to very large, depending on the particular image format you're using, for example. Reports, the same. What format are they in? What are they a report of? How many pages? Do they contain graphics? What sort of statistics and details do they have within them? Emails, again, they could be of any size. It could be very small, they could be massive, depending on attachments and all sorts of different things. So because of that, we've really got no idea or very little idea of how to predict how much storage space we're going to need. Because on any one day, we might have, as Shane said before, billions of transactions. How many of those are text files? How many of them are going to be video files? How many are going to be image files, as simple examples? This unstructured data, because it comes in so many different forms and sizes and values, very difficult to predict how much money, space, and resources we're going to need to store it, to process it, to analyze it. And so because of that, as we said, structured data, more streamlined storage process, unstructured, very up and down. And often, what typically structured and unstructured data are stored in very different environments. So we typically use data warehouses to hold our structured data, and we use data lakes to hold our unstructured data. And a data warehouse is simply a central repository for storing that structured data. They pull data from structured sources only, including things like databases and transactional systems and those sort of ideas that we posited before. So our point of sale systems, our booking systems, anything that's transactional, we pull into these data warehouses. They're mainly used for storage of the data. So simply exactly like a big warehouse would be, full of boxes. This is a big warehouse full of structured files. But they can also be used to analyze data and to develop intelligence, if you like. So useful outcomes and useful sources of information for businesses to base business decisions on. They can scale to very large sizes, and they can be used by hundreds of business users at the same time. So lots of different customers. And if you think about cloud providers that are offering data warehouse services, lots of customers can access the same data warehouse at the same time and get the benefit of that data contained within. By comparison, a data lake is the same. It's a central repository, but in this case, we're just storing raw, unstructured data. So whatever comes in, if it's not structured, if it's not a database file or comes from a database system, it's not an Excel spreadsheet, for example, it just, if it's an image, it's a movie, it's an email, it's some other custom generated piece of multimedia, it will pop into this unstructured data lake. And again, these things are massive. So they are literally capable of storing more information than most of us can probably imagine in our minds, certainly more than I can imagine in my mind. And these are becoming more and more common. And simply because the vast majority of the data that we pull into these big data repositories is that unstructured data. So we need lakes rather than warehouses. Of course, it's a horses for courses type approach. So if you're a business or an environment, so a industry that relies very heavily on structured data, then you're more likely to move to a data warehouse type model. If you're the other, so you're looking at lots of unstructured data and you're just pulling it from lots of different unstructured sources, then the data lake is the storage method that you're most likely to go off with. So as you can imagine, these store information from all these different applications and devices that are now ubiquitous in our lives. So all these IoT, Internet of Things, Internet of Everything devices that are connected everywhere, all these different types of information that comes from those. And I'm sure all of you could think of at least 15 or 20 different devices that are now connected to the internet in your own homes that somehow generate some sort of data. It doesn't have to be meaningful to you or I specifically. It may, we might look at it and think, well, what does that mean? But it may be useful in terms of an analytical process or a research process or some sort of statistical analysis. The last one, of course, is semi-structured data. So it sort of makes sense that this is somewhere between the two. So it's not fully structured, but it's not totally unstructured as well. It can't be considered fully structured because there's no specific relational or tabular data model. Okay, so you can't easily build relationships with semi-structured data, but it does include metadata. So that is data that talks about the characteristics, so describes the actual data that you've got. Not the contents of it, but describes attributes of that particular data. So things like its creation date, its author, when it was last changed, those sorts of details are included in that metadata. Now, this is because it's semi-structured, so it's got this metadata there. It is considered to be a little easier to uh, analyze and therefore come out with useful outcomes and to produce information from than it is to do that with unstructured data. But then it's not quite as easy as structured, okay, which makes sense because it's in between the two extremes, in between those two extremes. It simply doesn't have completeness of information that we associate with structured data. So in structured data, not only can we describe the contents of what's in a file, for example, but we can easily and definitively describe the way it looks and the way it is constructed within that file. Semi-structured, we've got a little bit of information about the different characteristics, but doesn't tell us the whole story. And in unstructured data, we really don't know what there is. It is so unstructured and so free fall that we can't really tell too much about it from an analytical perspective. I mean, obviously we can look at it and we can, if we look at it in file manager or something, we can tell it's an image file and we know it's this name and we can click on it, we can see what the image is. But in terms of the underlying zeros and ones, I guess, if you want to put in that, or the attributes in which we can analyze and pull apart, so the information we can pull apart from those files is more challenging in an unstructured environment. And there's some examples of what semi-structured data might look like. It's interesting that emails is included in semi-structured and unstructured as well. And that's something that we're going to talk about. Not sure whether it's next week or in week 3. So if anyone's noticed that, oh, I shouldn't have said that. Hopefully someone would have picked that up, but it's actually mentioned in both, which is interesting. So where can big data come from? You've probably guessed by now, pretty much anywhere. Anything that is connected to a network, and let's face it, most things are nowadays, can be a source of big data. Anything. Now, some of these things like medical records, for example. Now, there's lots of legislation around those, around the security of those, and who can handle them and who can do what to them. That doesn't mean that they're not in big data repositories. It just means that the whole world can't necessarily get access to them. And of course, remember that big data doesn't describe one all-encompassing system. It simply describes a system that pulls in sources of information or data more correctly from lots of different places, stores them in the one place, and allows you to more intelligently analyze and query that data set to come up with answers to questions or to come up with useful outcomes. Now, again, this is not exhaustive, but if we just look at the first couple, social media platforms, I mean, how many of those are there now? Many. IoT devices, how many of those are there now? Many. There are lots of transaction systems. There are obviously millions of customer databases floating around a place. Documents, how generic a term is that? Medical records, obviously a lot. Internet logs, huge amounts. Mobile apps. All of these sorts of things provide us with information. All of these things. You think about, let's keep it really simple. Okay, so you think about something like Facebook. Every time you click on something, every time you open something, you read it, you make a comment, you pause on it, you play a video, you look at a reel, whatever, all of that information is noted and it's analyzed. And then start to push out things that are of your like, things that you regularly, all of a sudden you'll see things popping up that are tailored specifically for you. And they think, oh, how do they know that? Big data. That's how they collect all that information, they analyze it, and they customize the experience to you as the viewer, engaging you more and making it more likely that there'll be more clicks, that they can send you more advertisements, that you might buy more stuff. It's all about the big data.
Might be a good spot to just check in for some questions, I think. Right?
Yes, go for it.
Let's actually have a bit chat about the elephant in the room first, because that's come up in about half the questions, which is AI. A number of people are suggesting, of course, that AI is, by definition, big data personified, because it uses big data to create the learning platforms for it. There was a specific question, though. It sounds like the schema could be integrated to some degree with AI. How do you see the role of AI and machine learning evolving in the context of big data analysis? And what are some emerging trends or tools in this area?
That's a big question.
I was going to say you might be well addressing this later on in the course.
Yeah, we will talk about that a little bit later on, but I will say, and I'll keep this to a niche thing because it's something that I'm actually involved in at the moment quite heavily. Um, so AI obviously has got a massive future in pretty much every industry that you can think of. Now, one application of that at the moment, and there was, I think the question also said something about machine learning. Is that right?
Yep.
Yeah. So one of the applications that I've been working with quite a lot in recent times is to do with biomechanical information or biomechanical data. So raw accelerometry data that we are, so that in effect is unstructured data because I can't even say that. Accelerometry data involves movement in all three directions, so up, down, left, right, backwards, and forwards. And we're using these accelerometry devices, they're just a little thing, and we put them on various anatomical landmarks on a person's body, and we get them to do these different varying tasks. And so we're trying to, well, it's working. We're training using that big data because you'd be surprised at how much data a single accelerometer generates for a given time period. So it's massive amounts. So if you think the ones we're using are sampling 1,000 times a second in all three directions, so it's 3,000 samples a second, and often the tasks that we're doing are 5 to 10 minutes long. So it's a massive amount of data. So what we're trying to do is take that data and using machine learning, provide ourselves with a single tool that will then be able to recognize different tasks just by the accelerometry data. So that's a simple that, and that is I shouldn't say it's simple because it's not, but it's a relatively straightforward application of machine learning using big data. Um, the actual AI side of it, there might be something that'll come out of that at a later time, but at the moment we're sort of looking at machine language. And look, this is with a specific sport in mind, what I'm working with at the moment. But if you think about the potential applications across the healthcare industry as a whole, particularly around exercise physiology, physiotherapy, rehabilitation, then the application for that just in that one industry is absolutely massive. Absolutely massive for providing better outcomes for patients, for improving um, treatment modalities, um, lots and lots of potential avenues. And that's simply in that health area or health industry. If you then think about how that might be applied to sport in terms of performance enhancements at the elite level, then it takes on another step as well. And they're just two specific industries that I know quite a lot about at the moment that are doing a lot of work in that area.
Yeah.
So there's huge application for it, huge potential application for it, absolutely.
Um, just one last question on AI. Must have stadium loads of data. Is that structured or unstructured or all of the above?
Sorry, what was that?
AI must have stadium loads of data. In fact, data lake houses, I believe it's a
Oh yeah,
problem for a
yeah,
lot of the companies just keeping up with the power requirements.
yeah.
But is that all, is that structured, unstructured, or is it everything?
It's everything. It's
Yeah.
everything. So there's just all just semi-structured, unstructured, structured, you name it. It's just all in the one repository. So oh well, when I say repository, it's all considered under the one umbrella. Yeah, yeah.
I'll do a
So
couple of
again,
the
we use warehouses for the structured, data lakes for the unstructured, but there's that ability to use the data from different repositories, put them together, which is actually exactly what this next section is on, this distributed computing idea.
Right. Couple more quick questions. Is it fair to say that unstructured data can be used for more varied types of reporting?
Yes, yeah, yep.
Great.
I would totally agree with that.
Mhm.
Absolutely. It allows you to, well, it allows you to interrogate it in a infinite number, almost infinite number of ways. Well, I'm probably sure it is infinite. I can't say that definitively, but in a lot more ways than you can with structured data, because think of it as being open-ended.
Yeah.
It's just open-ended. Structured data is as we said earlier, it's very specific and it's relatable generally to a single context or a small range of context, whereas unstructured data can be it's a bit like an open-ended question. It might apply to many different contexts and therefore many different questions and therefore provide many different answers slash outcomes slash solutions.
It's a bit like deductive and inductive reasoning. One last
Yeah.
question and then we'll move on. Are there processes or techniques which would convert unstructured data on capture to structured data and therefore reduce storage, make it easier to manipulate?
It is possible, but it depends on the unstructured data. Some unstructured data cannot be, there's no easy way to convert it into structured data, but there are some, and I think we look at some of those techniques in week 4. I think it is either week 3 or week 4. We'll actually look at a little bit of how it's possible to in certain contexts with certain types of unstructured data to convert it so that A, it's easier to analyze and easier to report on, interrogate, and B, is more efficient to store.
Great. We'll have a few more questions later on.
All right, no problem. All right, so last section for this evening is distributed computing. So the whole idea of this is to really spread the resource requirements rather than having one single all-powerful computer that tries to do everything. We spread the load. That's really all it's about. It's relatively straightforward. So it's a simple model in which we have components of a software system shared amongst multiple hardware platforms. And all this means is it essentially allows us to parallel process large data sets. So instead of having one device just hammering its way through a very large data set, we have multiple devices doing multiple tasks on the one data set, distributed across different platforms. The advantage of this, of course, is also is we can process, handle, analyze using different queries, different questions at the same time. So it's just taking a big data set, sharing amongst multiple computers. So same, if you like, overall software system. So software umbrella still uses the same idea software-wise, but hardware-wise, we're distributing it across multiple hardware platform with each of these platforms will have a mountain of memory, a mountain of processing power, and we feed it multiple tasks and we parallel process. There are a couple of different popular, if you like, frameworks or solutions. Hadoop is one. It's an open source framework. So being a framework, think of it as being a set of processes or software guidelines, if you like, which allow us to distribute our storage across multiple storage systems and allow us to process really large data sets across multiple processing platforms. It's got two components, which I won't go into detail now. There's a tutorial that I've posted up, or that there's a link to in the Module 1 resources that you can have a look at, but I'm going to talk about that in a couple of slides' time in a little bit more detail. So but basically it's got two components, a file system and then a programming model, which allows it to scale to very large sizes of data sets. The other one that we'll be looking at in the coming weeks is a platform called Apache Spark, which is really more around analytics. It's very fast, apparently very easy to use, and I say apparently because I've not specifically used it. And it supports in-memory computing. So that means it supports the ability to have our processing done in memory, which of course is going to speed it up rather than having it on distributed storage systems. Distributed computing is clearly going to be crucial as big data gets bigger. So the bigger your big data, the more distributed computing is going to help you. Parallel processing is the heart of it. So instead of doing one thing at a time, we're going to ask it to do multiple things at the same time on the same data set. That's always going to be not necessarily easier, but it's going to be more efficient. You'll get more output in a smaller time frame. But it's obviously expensive. It's going to be expensive. The more data you have and the more data you need to process, the more quickly you want your answers, the more resources you need to throw at it. Therefore, it's more expensive. Now, both Hadoop and Spark are pretty efficient. Okay, so if we think back to the dawn of big data a few years ago, couldn't tell you how many, but a few years ago now, As with any sort of new concept or new thing, we're eager as humans to use it. Oh, look at this. Look at the great advantages of this. And we have to work out how we can do it more efficiently and in a better way. Hadoop and Spark are a result of that process with big data. Okay, so we're starting to become more efficient. We're starting to become better with our parallel processing, with our design of our distributed computing systems, and it's starting to become more achievable. So an example using Hadoop here, and this is a tutorial, as I said before, that is up on the Moodle site for you to have a look at some stage. It's it's an actual document that you can go through, and this is an image from that document. And it gives an example of what Hadoop is all about using an analogy of a restaurant. So what we're talking about is initially we have a fellow decides to open up a restaurant. He's got one cook and he's got one refrigerator. They call it a storage shelf, but it's effectively a pantry, or you call it a pantry if you want to. So we've got one cook and one pantry. Now, while he's got a small restaurant, say he's got ten seats in his restaurant, the single cook can keep up with 10 orders at a time. No problem at all. He can do that. Then he starts to get a little bit more successful and he decides, well, we're going to upgrade to 20 seats, 30 seats, 40 seats, 50 seats, however many. Starts to scale. There'll come a time when that single cook, so processor, think of him as being the processor or compute system, he won't be able to keep up. He won't be able to deliver the meals on time to the people as they're ordering. It's not going to work. And so what do we need to do? We need to add another cook, a separate cook. So now we have two cooks. So we can now get our orders out faster. So we can scale to a greater degree in terms of customers now coming into the restaurant. But then we'll get to another time where the pantry won't be big enough. We won't be able to have enough data or ingredients in that pantry to be able to service the needs of the customers coming in and ordering. And so we add another pantry and so on. And that loop continues. So as we get more customers, we need more cooks. As we need more cooks, eventually we're going to need more pantries. And it just goes round and round and round, getting bigger and bigger and bigger and bigger. And so the analogy he then uses is that what we do is we have split our chefs into two groups. So we have our chefs on the pass who are doing the final they're doing the final finishing touches on our dishes and doing the final, little bits and pieces to make them look beautiful. And then we have our waiters who will come and take them away. And then behind those, we have all the other individual cooks. So the one on sauces, the one on desserts, the one on fish, the one on meat, the one on vegetables. We have the prep chefs that do the mise en place, so do the preparation. You have all these different people working in the background, and they compute or take the ingredients out of all the pantries that we now have. They make the different components, they put them all together, pass them to the head chefs or the CDCs, who then put the finishing touches on them and then send them out to the customers. So that's the sort of analogy that Hadoop fits into. This HDFS, Hadoop distributed file system, is analogous to having lots of different pantries. We've got lots of different storage spaces, lots of different ingredients, all that unstructured or structured data or semi-structured data that we have in our pantries. We have our different distributed compute systems, so our line chefs that are our distributed compute systems that they go off and they find all these different ingredients. So someone will come in and you think of an order as being like a question. So someone's asked a question to interrogate the big data set. That comes into these line cooks who go and find all the different ingredients, so all the different data that might make up a possible answer to that question. And they do their little part of processing their little individual part of the ingredients from their individual data store, and then they pass it on to the person that presents the answer, so the interface, so to speak. And this is sort of, if you think of it that way, this is sort of how AI fits into this sort of equation. So you open up something like ChatGPT and you ask it a question, what happens? Okay, it goes off and it interrogates all these other distributed systems and says, hey, I've got this question. Can you please give me an answer? And they go off and they interrogate their different data stores and they come back and they collate everything together and they present it to ChatGPT, who then gives us the answer. Now, the back end of it, I'm sure, I'm not an expert on how the back end of it works, but I'm sure is much more complex for that. But that, in a nutshell, in the simple terms, is the idea that we're looking at in terms of this big data and how AI can interface with that. All right. That's all I really wanted to say. Unbelievably, I've finished in just under the hour, which I think is a world record for me, Shane. So
That
what
is
other
amazing.
questions have we got?
Okay. Does web scraping fall on unstructured data?
So sorry, what was that? Does web
Is
scraping?
web scraping unstructured data? I suppose it depends what you're scraping, really, doesn't it?
Yeah, it does. It does. But by and large, it will be unstructured data. Yes.
Okay. Nice to get some easy ones. In big data, if because there's a high volume of data reporting, does that mean we can't do real-time reporting? Or, and then sort of part B of that question is, can we identify how long we've got to wait before we can actually do something like near real-time reporting that's going to be accurate? I suppose it depends again on the application, really, doesn't it?
Yeah, it does. Depends on the application. It depends on how many resources you've got involved in it. And I think the thing to really contextualize here is that when we talk about big data, as I said, I think at the somewhere at the start of the session, is we're not talking about one single repository of data that covers everything that's out there. Okay, so if you think of ChatGPT, right, or Google's whatever is called Bard or something, and there's multiple AI engines, if you like. They all have their own big data set in the background there somewhere that they're looking at that pulls from different repositories. Now, sure, there'll be a lot of repositories that will be similar, but they all have their own smaller subset of the entire data set that's out there in the world. If we were just considering, if we said, okay, there's only one instance of big data and it considers every single piece of data that's coming from every single device that's connected to the online world, then you would have no hope in hell of doing real-time reporting. It would just be impossible with a data set that large. Having said that, it also depends on what questions are you asking?
Yeah,
What are you asking about?
because we are doing real-time reporting on things like electricity and
Yeah,
metering, all of
absolutely.
those sorts of applications.
Absolutely. We can do real-time reporting on that because yes, it's a it's considered big data, but it's big data within a very small context. So if you say each of the power companies has access to their own power electricity data, they can do real reporting on that because in the overall scheme of things, it's not a massive data set compared to the hardware that they've got to be able to process it. So real-time reporting then in that case becomes relatively easy. And in most even enterprise organizations that use these type of big data systems for and really if you think about it, you don't have to have Splunk to be considered big data. Yeah, I mean, big data is just a repository of data that you've got from multiple sources. So it could be anywhere. Most enterprises will have some sort of reporting engine that will be able to real-time report based on their own context. But if you were trying to, for example, do real-time reporting of every single traffic flow on the internet, then you're not going to do it. So it
No,
depends on context.
yeah.
And what was the second part of that question? Sorry,
Uh, I
was there a
don't,
second part?
I don't think there was a second part of
Oh,
that
okay.
there.
Sorry. Yep.
That's okay. The first one had a second part. If you want, here's one you'll enjoy. What's the ethical considerations for using this data in terms of one, sustainable storage, and two, bias analysis, selecting data to produce the result you want?
That's an
It,
excellent question.
it's a double banger, that one.
Yeah, it is. It is. In terms of the storage, so ethical requirements on storage. Okay, so that's going to greatly depend on the type of data that you're talking about, clearly. So if you've got PHI or PII, so private health information or personally identifiable information, then there are serious ethical constraints around that depending on the industry that you're in. Some of them are legislated and regulated, and others are not quite so much. If I talk about if we keep it to a smaller context, say education, if we look at research projects, for example, that are using that collect some sort of biospecimen or do some sort of human inter or animal interaction, then the storage of data in those cases, there are very strict ethical constraints around that that are very fiercely maintained and policed in the if we're looking at something like Chat GPT, for example, which doesn't have access to those sorts of information, then the ethical dilemma is not really so much of a worry. The bias one, though, is a very interesting one. Because as most of us are probably aware, depending on how your integrity is as a researcher or as a developer or as a business or or any politician, dare I say, depending on what your integrity is like, you can certainly massage large sets of data to be turned into whatever outcome you want them to be. And I don't know that there's any particular way that you can legislate or protect or stop that from happening, to be frank.
Yeah, absolutely. And I wonder if the ethical question was also relating to the ethics of having such large scale data storage and the energy and other resources it chews up as part of it, which is, a complex
Oh,
question to
that's an
answer.
interesting point too. Yeah, no, it must have been I hadn't thought of that, but yeah, that's an interesting point. Yeah.
Do you feel like a whole pile of questions about the cook analogy? Because there are a number.
Oh, there. Okay, go for it.
Okay. With the example of the chef, isn't this structured data as there is a menu and ingredients will be stored in specific places in the cupboards?
Yeah, in that example it is, but it's just an analogy. It's not a strict adherence to structured, unstructured, or semi-structured. What you sort of think of it as like so in that example, yes, I would say you're right. There is it's very structured in that particular context. Yes, that would be a fair assumption to make.
Okay. If
But
one,
the idea that's really just to present the idea of distributed computing.
yep. Yes, let's not push the analogy too far. But on that note, if one of the cooks in that example takes a sickie, would the entire customer's order fail? Or would there be a redundant or some backup plan in the Hadoop processing to
I
fulfill
love the way
the
that question is asked in a tongue-in-cheek manner, but it's actually a very sensible question. So, yes, if one of the compute systems was to fail, then it would reduce the capacity of the distributing computing platform. But having said that, any platform, obviously worth its salt, is going to have sufficient redundancy built in. Otherwise, there would be a performance hit. Absolutely.
I just realized I was muted. How do you approach the challenge of data scalability, particularly when dealing with exponential data growth?
It's a challenge. It's a challenge, and this sort of gets this. I'm not sure whether I want to start down this path, but it gets me into an area of chagrin, I guess, something that gets on my goat a little bit, or would if I had a goat. And that is that, look, it is a challenge, absolutely, in predicting, particularly with unstructured data, predicting what we're going to need as a whole. Okay, so if you're talking about specific enterprise who collects unstructured data about customers or products or or whatever it is that they're collecting information about from various sources, it's not quite such a big challenge. What's challenging is if you look at massive systems like things run by Google or ChatGPT and the amount of information that's coming into them. The scalability question is a very difficult one to account for. So what you'll find is I guess the answer to that is that the enterprises who are or the managers of the systems that are going to take in that much data have access to so many resources and so much money that again, it's not an overly challenging problem to them. One of the things I think, and the thing that gets the problem I have with this sort of discussion is that a lot of people have been talking about the death of networking, saying, with software-defined networking and using AI in networking and big data systems in networking, that the age of the network engineer is gone and they won't be used anymore. But that's complete and utter rubbish. And this again leads on to the fact you're talking about with scalability as well, is that we're always going to need people, whether that's network engineers, software engineers, compute systems, so server engineers or whatever, to help scale these systems and maintain these systems upon which big data and AI and these intelligent systems now rely on quite heavily. So I guess, look, to be specific about the answer to your question, it again depends on which context you're talking about. So if you look at big data as it applies to individual enterprises, then it's unlikely that any single enterprise is going to be overrun with so much information that they won't be able to scale in a sufficient time frame to be able to take that in. If we're talking about big organizations like Google, for example, again, I'm not sure that it's too much of an issue to them, given the amount of computing power they have around the place and the amount of spare capacity that they have.
Yeah, it becomes a question of cost then, doesn't it? And resource chewing
Oh,
up.
absolutely. And I mean, as I said, that those that are the sorts of companies that are going to be in that situation to be taking in that amount of data are more likely to have the finances and the ability to scale rapidly.
One of the people in the chat earlier said that they were working in a Hadoop environment, which went from 100 racks in the data center to 1,800 in the space of about a year,
Yeah. Yep.
which is about where it's at. Unstructured data is expensive to store and process. So how would you how would you try and bring the cost down or change the data to make it more cost effective?
Oh, that's a question for someone far more intelligent than I. Uh, as I said, in later on in one of the subsequent weeks, we're going to look at some strategies that we can manipulate our data and or condense it in order to convert from more of an unstructured to more of a semi-structured, and in some cases structured, which then increases the efficiency of the storage and reduces the amount of processing required to be able to interrogate that sort of data. But where we've got in purely unstructured environments, it's a matter of, I mean, storage systems are relatively cheap. Again, if we contextualize to enterprise level, not talking about global level, but if we're talking about enterprise level, then storage systems are relatively cheap, depending on the type of storage system. So then that capacity issue is not quite as scary as what it might seem. But there are ways in which we can turn our unstructured data or manipulate it so that it appears more as semi-structured or structured data. But we'll talk about those in one of the upcoming weeks.
Great. We will shut the questions down in about another minute and a half to 2 minutes. I've still got quite a few here to answer, though. Nicole comes from a records and information management background, like I would imagine archives or librarianship or something. My concern with big data is how do we manage retention and destruction? And I would imagine that's something to do with how you manage the decision making about what you decide to keep and how you vector that.
Yeah, look, it's more around in terms of the management and as you said, the destruction of it, that's more of a policy thing. So all the tools are built into big data to be able to store it, label it, classify it, manage it, and delete it or destroy it, whichever way you want to look at it, in any way you see fit. It's really there's still got to be some underlying guidelines, policies, regulations, legislation, whatever, depending on your area that are going to dictate what you have to do with it. The capability and the functionality is there. It's just a matter of what you choose to do with it.
Okay, how can we effectively mitigate unauthorized access in big data environments, considering that there are often, well, this is answering the question and asking it, but there are often inadequate security measures as data volume grows.
Oh yeah, indeed. It is going to be a challenge. But we use appropriate access control methodologies. So we use, multi-factor systems. We use different multi-factor authentication systems to be able to do that. I mean, at the end of the day, yes, if you look at you look at publicly available big data sets, then not so much an issue. What we're really talking about is security around, specifically around information that is either has some sort of regulation or legislative requirements to keep it private or secret. And if that's the case, then there should be appropriate authentication and access control methodologies built into those systems. If there's not, then that's a failing of the either bespoke programmers or the people that develop the systems or those that are in charge of actually maintaining the security of it. So, and this is something I think that it's a bit like the old chestnut around saying that wireless networking is less secure than wired networking. It's simply not the case. The same issues are representative in both media types. It's just, and the same mitigation techniques, the same secure techniques are there. You just need to apply them. And the same applies to this. Whether you've got a small database or a massive system, it's you need to provide some sort of regulated, protected method for accessing that system. So the methods are there, the principles are there, the toolkits are all there. It's just about putting them in basing what your requirements are and implementing appropriate measures for your requirements. So it's actually quite a simple answer, really. It sort of depends.
Yes, indeed. Here's one a little bit different. Is CrowdStrike using distributed computing, and is that contributed to why it caused so many problems in so many multiple systems, including at our company? We lost only one laptop though. They got all the rest to not upgrade.
Well, if you look at that, yes, it is. It is a form of distributed computing, because let's face it, what is it doing? So, CrowdStrike, you buy an MDR package from them. They put an agent on all the different devices that you want to be protected. That agent collects that information using the power of that particular device, and then sends it across to CrowdStrike, which then and stick it on their storage systems. They analyze it using their different systems, which there's not a single system. There's a whole bunch of systems that parallel process all of that information that comes in from all the customers. So absolutely, it's a distributed system. Did it have anything to do with what happened the other day? As far as I'm aware of what happened, the way I understand it, no. It wasn't specifically because it was a distributed system. It was specifically because a driver update didn't go as planned. But having
Right.
said that, had it not been a distributed system, that is not putting agents on the desktops, then it wouldn't have happened. But then you could also say, well, if they don't have agents on the desktops, then you're not buying an MDR response. So,
Yes, and it does cause to remind us how dependent we are upon automated processes that happen in the background.
oh, absolutely.
A couple of people are sort of asking is how much data is big data? I'm just summarizing those questions.
How much data is big data?
Mm.
Big data, if we go back to our definition, big data in whatever context you're talking about, because it'll be slightly different depending on your context, right? So if you're an enterprise, big data, what where you go from being data to big data, so the tipping point, if you like, is going to be much greater than it is if you're a small business, okay, a smaller enterprise, for example. So
Yeah,
if we go back to our definition, the tipping point between normal data, I guess, or I don't know, what would you call it? Not big data, small data? No, I don't know.
average
Whatever
data.
data and big data is when you get to the point where your inputs are so great that you can't analyze, report, and effectively use it using simple systems, your normal everyday regular applications. Once you get to a point where you need some sort of distributed platform to analyze and use those different data inputs, that would be the point where you would call yourself, say that you're using a big data system.
I can think of it a bit of an example in that every so many organizations keep data that doesn't seem to have any application at the moment beyond its intended use. For example, tolling on freeways. If you take the toll times of the freeways, that would in theory be a way of managing speeding on freeways, but they haven't actually got to that yet.
Yep.
Certainly not in Australia, because you just measure the time between the two tolls and you get an average speed, which
Yep.
does make it is a fairer way of measuring speeding too, because it will get the people at speed consistently. They do it in New South Wales already to some extent, but they have specific cameras for it. And back in the day, when that first came in, we had people that would actually stop in between those two cameras for
Yeah.
about half an hour to make up for the fact they've been speeding the whole time.
Which is kind of stupid, really.
Totally, but they weren't speeding to make up time. They were speeding because they like to drive their trucks fast. This
Uh,
was uh, this was in
well, that's,
the
as you
early
say,
days of
that's all
tracking.
up the Hume Highway.
Yeah, but you could do that in sort of different ways. But that's a thing about unintended uses for data collected for purpose A being used in purpose B, and that becomes big data because there's so much of it.
Yeah, correct.
Uh, what are the job prospects for those interested in having a career in big data?
Oh, I think they're pretty much unlimited, really. I mean, it's not going to slow down.
Hmm.
Let's just put it
Big,
that way. It's not going to slow down. It's like saying, what are the prospect? Would I be safe if I go into AI? Absolutely.
yeah. Or
Anything that's going to do with data processing, analytics, any of that sort of, yep, go for it. You'd be completely safe for the foreseeable future. And I have no doubt, like if I use my own example, when I first started working in this industry just over 30 years ago, there was jobs that existed then that don't exist now, but there are jobs now that grew off those jobs way back then. And now, of course, there's things that I never even dreamt I'd be that I would have worked with when I first started 30 years ago that now worked with for 10 years. And things just keep building on that. So if you were to go into AI or big data now, maybe in 15, 20 years' time, you might not specifically be in that field, but I could guarantee you that you would be in some sort of offshoot. So I think you're pretty safe if you head off in that career direction.
And the same with what you were saying about networking before. Without people building the infrastructure, there isn't any AI, there isn't any big data.
Yeah, absolutely. I mean, particularly if you look at, as you said, AI, I mean, the bandwidth requirements for that networking wise are absolutely ridiculous. Um, yeah, so I mean, stick with network. Networking is a great career. You can do that too, and you just apply it in different ways now.
Yeah, absolutely. We will keep going for about 2 or 3 more minutes. does distributed computing relate to elasticity in cloud computing?
Oh, it depends on whether the elasticity relates to a single set of processes or a single purpose, or whether you're just expanding to add different services. So it can, yes.
Okay. Do Cloud Era and Teradata use Hadoop frameworks, or do they have their own setup,
So run that by me again. Do Cloud Era and Teradata, do they use Hadoop framework at the back end,
or have
or
they
they have
their
their
own
own framework?
frameworks?
I actually don't know the answer to that question. I couldn't tell you. I'm
I think
sorry.
somebody else mentioned earlier that Cloud Era definitely uses Hadoop, but I could
Okay.
be wrong.
Yeah, that may do. I couldn't answer that off the top of my head. I can find out for you, but I couldn't answer it off the top of my head right now.
It's probably a good time to remind everybody, which I didn't before, that they should all be looking at the forum to ask questions, chat amongst yourselves, and see what else can come out of it. Because a lot of the good activity happens in the forums on learn.itmasters.edu.au. I've also noticed a couple of people have not got their passwords at various points. That may well be related to the period of time when the Moodle platform was under maintenance. We were still getting forms through, but we weren't able to send the passwords out. So there will be a little bit of that to catch up with. One last question. Let me have a think here. Somebody's asked, what scale of big data have you worked with? It says in terms of PB, which I assume might mean personal business, or
It may be. In terms of scale of big data, the biggest scale of data I've currently worked with is what I was talking about before, is that accelerometry data in research on a specific sport and specific movements.
yeah,
So that is when we're talking many terabytes of data. So it's not, extraordinarily large, but that would be the level I would say at the largest level I've worked on that I can think of. I couldn't think of anything in the past that would necessarily be classified as big data. I can't think of too many times where I did used to work in IT. Yeah, I was working in IT networking at a financial institution of fairly large size that did use distributed computing, and I guess what you could classify as an early idea of big data, but I wasn't necessarily specifically involved with that. I was just doing networking at that stage. So in terms of direct working with data, yeah, it would be that accelerometry data I was talking about before.
fantastic. Well, I think it's time to knock off for the evening. Thank you, everybody, for coming along. There's a couple more questions there. A lot of them relate to giving examples in specific areas, but I think that will come up during the course of the coming weeks as well. So there will be lots of examples as we progress. But as I said, thank you everyone for being with us tonight. We look forward to seeing you next Thursday. Big thanks to Lil for keeping an eye on the chat and making sure everyone is nice to each other. And of course, Matt, it is fantastic to have you on board again. It's a real pleasure. It's a fantastic night.
And also, obviously, thank you to you, Shane, for being the excellent MC that you are.
I'm the pinch hitter still. We will get Jack back, or we may even look for somebody else at some point. But who knows? Anyway, same bat channel, same bat time. Look forward to seeing you all next week. Thanks again.
Good night, everyone. Thank you.
Good night.